Okay, so we will start the course. Let me check. Chapter 9. Okay. All right. So we will start from, this will be chapter 10. This is, we call the parametric equations and polar coordinates. Okay, as I mentioned before, so this is the structure. So calculus 1, we learn about the single variable calculus, okay? Which means we have our functions and we have just one variable most of the time. If there is like more than one, what we can do is we can approach with implicit. Okay? We can approach with implicit. If more than one, implicitly we can take on and we can still differentiate with the implicit differentiations. Okay? So differentiate implicitly. Okay? But in calculus 2, we will have multi-variable calculus, which means that you will directly derive or integrate. Directly, if you have x, y, you will directly use derivatives to derive. Okay. We call this is partial. Okay. But before we are going to go into the partial one, we can look first some idea on how we can build or we can set up the components. Okay, first the components. Okay. So imagine you have the curve C. Okay, if you have the curve C like this. Okay, so imagine this is without any additional terms here. What is this? You just draw the curve C. Okay. So in the single variable, it seems that if you have this, it's not really defined if we are using the definition of function, right? Because we will have some part that is we are using the vertical line. Okay? If we take the if you take this, we have 3 points that is on the same axis. Right? So it's not ideal as a function, but in terms of if we are adding additional variables like t here, and usually if you learn physics, you will see some trajectory like this one, the distance, and they will add time. Usually you adding the time, right? If we have this additional variable, this seems possible because in every t, you will change your x and also your y, right? So this we call the parametric equations. So or just parametric, that's okay. Parametric means you will have additional variables. We call it the parameter. Adding a parameter to define a function. Functions or equations. Okay. So we will have, let's say x, we will have a function of t, and also y is a function of t. Let's say it's the x is f, y is g. Okay. So we can plot t, x, and y. Okay. So we can set up t from, let's say t we can set up from 0, 1, or even from -2 if we can have that as well, -1, 0, and so on. Okay, because t, it can be anything. Okay, t is not essentially a time; it can be anything. Okay. But I think it will be easier if you interpret t usually time, and this will be a position. Easier to understand. Okay, so that's the parametric. Okay, example. Okay, we can set up this the curve. This is okay. I haven't write the x is t squared minus 2t, y is t plus 1. And if you look here from this parametric x and y, we can also exchange and maybe simplify the equations into Cartesians if you would like. So we can have the t. So t is y minus 1, right? And we can substitute and taking this into our parabola equation, right? Which is, you see that it's y squared, and it's perfectly the same thing here. And we are moving -1 here. And if you want to solve this and simplify, you can also do that as well, and you can see the parabola. If you would like to check this, okay, so we can eliminate or remove the parametric, and we have only the parabola equation here, like this one. if you see the picture and also the equations, there is no restrictions on t, so it can be extended for long period, for longer curve around that. So you can have like 4 or 5 and unlimited weight, and -2, -3, -4. Okay. So sometimes we can also restrict to make sure that we can only observe that. So probably we can restrict it the t. We restricted the t up until like that, maybe -2 until 4. Or maybe 0 to 4, that's also possible. Depends on the situations, depends on the case also. Okay, so let me write one more time. So we can have we call the initial point this A, and the terminal point this B. So this will be the FA and GA. This is initial point, and this will be the terminal point. Okay. Another example on some parametric is you can have a circular like this one, a circle. It is not yet polar, but we can also write in terms of a parametric. Okay, before we continue. This will be your TA for this semester.
My name is Ilham. So you can call me Ilham. This is my Chinese name.
So you can introduce maybe some background.
Actually, I come from Indonesia and I study master in here. I took mechanical engineering. Did you guys interested about the mechanical engineering? Yeah, maybe you can continue. You can ask me about that, and also, yeah, the important thing is calculus.
Maybe some laboratory or
Oh, yeah.
any.
My laboratory is robotics, and my project is about optimization method. Yeah, it's related about the design and mechanical strength and mechanical properties. Yeah, if you guys interested about the robotics, yeah, so it's in my lab.
Okay, so you will be having a PA class on Thursday, right? The Thursday class. Okay, so this will be the another way to look at, okay, if you have the parametric in terms of 0 and pi over 2, pi, 3 over 2 pi, 2 pi. Oh, I even write the equations. Sorry. Let's observe this in terms of the circle equations, and we can write as cos squared t plus sine squared t. The parametric is this and this, and the t is from 0 to 2 pi. Okay, since the circle is just 0 to 2 pi, if you add more 3, 4, 5, it will be just circling around. So it's not a problem. So we can just write 0 to 2 pi. So we have cosine t, sine t, and we can use the circle equations to connect this x, y, and then we can have this equations, and we can write this actually in terms of x squared plus y squared equal 1. Okay. And if you look at this, there is no t mentioned here, right? We eliminate t. So basically, in some problems, like the parabola one, we can eliminate t and we can look on the whole equations without the parametric. Like this one also, cosine t, sine t, we can eliminate t as well. Okay? Just a few simple examples. Okay. Maybe let me give you another one. Okay. So if we have x equals sine 2t and y equal cosine 2t, and t is from 0 to 2 pi. And again, with the same process, we can have this. The difference is the parametric. The first one is just t. The second one here is 2t. So it's circling around. Okay? But the picture, how it looks like, is the same, right? Okay, I think the other part is just an example. Okay, let me move to the next slide. Okay, let's say we have this. X is sine t, but y is sine squared t. Okay. Okay, so first thing, if we look at the y, if we look at the curve or the equations, it's sine squared t, which is sine t, and then you have squared like that. Okay, so we can write this as just a parabola equation. Okay, okay, and then what else do we need? Remember that for sine, we will have the minimum and maximum point, right? So we will have so if you would like to draw this, and let's say this is the This is -1 and 1. So this will be -1, 1, and this is 1, 1. So we will have movement from this point here to here, and also from here to here. And this will be the sketch of the curve. Okay. Let's skip this one. Okay. Let me draw the okay. Imagine you have the circle. Okay. Let's observe the first circle, the left one, and let's make a point. This point P. Okay. Okay. Imagine the circle. The first one here is moving. So imagine this imagine this circle is moving. Let me make another. Okay. Circling, and then make another position here. Okay. Of course, if you imagine this P, it will be also moving, right? Okay. So imagine, and probably as the circle moves, let's say the P is changing to up here, maybe here. And you have another scenario after 2. You have third scenario. Let's say let's say maybe around here. And if you connect all the possibility when you move the circle, and you look at how the P will be changed, the position of P, and you connect all the points, like maybe at here, it will be moving, and then you connect all the trajectory of P, it will be like that. Yeah, it should be around here. Let me just change the P to make it more clear. Okay. This trajectory, the red circle, if you move the circle, go for some distance, it will be having repetitions of this trajectory. Okay. We call that trajectory as cycloid. If we observe and getting some parts a little bit more clear, okay, we can observe one circle. Okay. And let's say we have let's say we observe P when it is like this, okay? And let me draw this cycloid like that, okay? And let's say we have a center. The center, let's say this is C, okay, the center. And let me draw the radius of the circle. Let's say this is the radius, okay. And from C to the ground, we can also have a distance. Let's say this is D, okay, the distance. And let's have another point here, it's Q. And we will have an angle theta, okay, here. And let's point out this is the origin, this is x and y axis, so we have still at the Cartesians, okay. So we have an angle from this line and the radius. We have center, some point P in the middle of this distance, and the ground is P. Okay, now to observe this and how the cycloid will be. So what is the idea here is we want to know how the cycloid moves, or how the position of cycloid in terms of the radius, in terms of the theta, if we can observe and maybe identify all the distance here. So if we take this P and we can have some relative distance. And let's say this is, let's just take it as y and x. So we want to know x and y. Okay, we want to know x and y. Okay. Okay, first thing, if you see is OT, okay, it's OT. The P, before it's moved to this point, it was on this, right? Okay. Imagine that the P was going up here. So the whole thing here, the arc of the circle, PT, is start from here, right? It's all touching the OT. Right? This PT is touching the ground OT, right? So that's the first assumption. This arc will be the same as the distance of OT. That's the first assumption. Okay? So let me write the arc of PT. The arc of PT, which is the circle with the angle theta, this is having the radius r, angle theta. So the arc will be r theta. Right? Okay. Remember that? So RPT is r theta. Okay. And the distance of OT is the arc PT, which means that the OT is r theta. So we can have this. This is r theta, right? Okay. This one here. So if you want to know this x here, the position of P, we can have the OT or the r theta minus with this, right? PQ. And we know the PQ from this triangle, right? So we can write the PQ. Let me use the different color. So PQ is R signed, right? Okay. So X is OT minus PQ, or X is R theta minus R sine theta. Okay. For y, the distance y for the speed means that this CT minus the CQ or QC. And we know that because we are having a circle, although I'm drawing a little bit like ellipse, but it should be circle. Okay. So this radius, this is also the radius, the same distance because it's a circle. So the radius minus the r cosine theta for y. Let me move this a little bit right here. Okay. So QC so y is r minus r cos. So or this become r So this equation here will be specifically saying how the cycloid moves or having a position, position of the cycloid. Okay? So to identify how the cycloid position, we can check for some theta from 0 to 2 pi how it's moving, and we can also set some radius, okay, to get the value for the distance. Actually, in the textbook, there are some of the shape or parametric that is specified, but I don't want to go into more details about that. At least for the essential parts, we already tackle, and this is just the example on how we can set up the parametric for a cycloid. Okay. So let me move to another introduction to the calculus. Okay, so all the things here is this introduction about the parametric. Okay, about the parametric. So let me just go to the calculus part. Okay. Okay, let's start with the suppose that functions f and g, they are differentiable and we have the parametric x and y for some function f g with parametric t. Then, okay, sorry, should be where y is differentiable functions of x. So this should be having these terms. Okay. So aside from the parametric, this y is actually also a function of x. Okay. So if we have this assumption, we have x, y, both are parametric function of t, but y is actually a function of x. Okay. Let's say we have this statement. Okay, then the tangent, okay, the tangent based on the chain rule or maybe let me write more with black color. So dy over dt is dy over dx okay, based on the chain rule, we can have this set up. Right? Okay. And we can write this as, so let me write, if dx over dt is not equal 0, we can solve solution for dy over dx is dy over dt divided by dx over dt. Okay, that's the first equations. So the slope or slope of tangent will be this, dy over dx. Okay, let's say we have a curve that defined by the parametric as x equal t squared and y is t cubed minus 3t. Okay, show that the curve has two tangents at point 30 and find the equations. Okay, of course, if you would like to eliminate the parameter, the t, you can do that as well if you want. So we can have the t is the square root of x, and we can put here, and we can have some calculations, and we can also find the tangent. Okay, find the tangent as well, find the slope. But instead of that, we can directly go for just dy over dx equal dy over dt defined by dx over dt. This is to find the tangent from the parametric. Okay. So if you have the parametric, you can derive each functions with respect to t. You derive first, and then you just define two. We can write first for t equal plus minus 3, x will be 3, okay? And y will be we can have the 0 here. So this is just to prove if we plug in the positions. Okay. So we have, okay, at 3, 0, we have two values of t that is specifically stated that we have two tangents, right? Okay, because we have the two parameter, okay, that is making the 0, okay, for our equations. Okay. Okay. So the dy over dx is dy over dt divided by dx over dt. So dy over dt will be 3t squared minus 3 divided by 2t. And we can set up for two different value. So for t equal positive square root of 3, and for t is negative square root of 3. So this will be dy dx. Six divided by this is becoming square root of 3, right? And the other one will be just taking the negative, it will be negative square root of 3. So we have the slope or the gradient. Then the tangent line, we can just set up from our equations here. We have let me move a little bit. The size of it, maybe here. So at x equal 3 and y equal 0, we will have y. The gradient is first is square root of 3, x minus 3, and we have so we have two tangent line here. Okay. 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 Let me move to the next slide. It's still the same question. Okay, let me write the curve equations. Find points on curve where the the tangent is horizontal or vertical. Okay, so for horizontal or vertical tangent, if you remember, okay, we will have this horizontal tangent. This is if the d over dx is equal 0, right? Okay. So how this happens in our parametric? So if we remember, so this should be 0, right? This one, the top one here should be 0. This should be not equal 0. It should be a number, right? Okay. So this should be a 0. So from our equations, we have dy over dt is 3t squared minus 3t. So at t equal 1, the equations will be 0. dy dt is 0. Oh, sorry. Should be minus 3. So t squared is equal 1, so t is plus minus 1. So when t is plus minus 1, then should be the points are 1 and minus 2 and 1 and 2, right? If we plug into the parametric, okay. This is the horizontal tangent. Okay, if you maybe having difficulty on vertical or horizontal, if you can check, just make any random, just a parabola like this. Okay, just a parabola. At every point you will see it's going to have some slight changes on the slope, right? It's going positive and then 0 when it's horizontal, so dy dx is 0, and then going down is the negative. Okay? The vertical tangent. So when is our slope is vertical? When? If we have, for example, if you remember we learn about the limit, okay? We learn about the limit. If we have maybe like that, okay? Maybe the exponent, or maybe you remember the tangent, okay? some part you have infinite, right? When you're going here, it's vertical. So you have some infinite number, right? So what do I mean by that is, at this point, if you are remembering the limit, you have something divided by 0, right? You have something divided by 0, maybe a constant divided, or c divided by 0, or some number here divided by maybe x divided by 0, or something like that, and you have the concept of limit, you know, and you can have your vertical line. Right? So the same thing you apply to the vertical tangent. So in vertical tangent and parametric, this dx over dt should be 0, and this should be not 0. Okay? That's how you can get a glimpse or an approach to a vertical tangent. Okay? So this should be equal 0, and this is not 0. Okay? So the dx over dt, let me write here. So dx over dt is 2t, which means if you equal that to 0, then your t is 0. When your t is 0, what will happen to our positions is just 0, 0, right? Just origin points. So the points, the corresponding point is just 0, 0 for the vertical tangent. Okay. So a little bit review. Okay. Horizontal, vertical. Okay. Okay. So let me give you a little bit time to, if you want to write some notes. Okay, the next question from this particular parametric is if you want to know the concavity. So that's a little bit tricky from calculus 1. Concavity, whether it's upwards, downwards, you need to have the second derivative, right? Second derivative. Okay. So let me write the questions here. So determine the concavity. It's concave upwards or concave downwards. Okay. This or this. So concavity, we need to have the second derivative. Let me write the equations first. Let me write again. The equation is t squared and y is t cubed minus 3t. Okay. And dy dx is dy over dt dx over dt. That is dy over dx. Okay. Now what is the second derivative? second derivatives from this dy over dx. Any idea? Or we can just derive this. So 6t divided by 2, 3t. Is that okay? What is the second? Any idea how? Or what? What is the second derivative? This is probably one mistake that will happen if you don't really pay attention to what is the definition that, or what is the concept that we are going to prove on here. Okay? But first, let's go back to the definitions. Okay, the definition here that is stated at the first or at the beginning of the calculus in parametric. Okay? So, first assumption. You have x and y as a function of t. Okay, that's the first. The second one, the y is function of x. Okay. Okay. So if you have some connection from x, y to t, okay, you can differentiate both of these with respect to t. No problem. And you can also define the chain rule from here, right? You can define the chain rule from here, and you can have the dy over dx. The same problem in calculus 1, dy over dx, to find the slope, to find the tangent line. It's the same problem with calculus 1. The difference is you can have the connections with the parameter, right? Okay. Now, if you are going to have the second derivative, if you directly derive this, and then derive also this, another one, right? It means that you broke the rule here, which is y itself is function of x. What you can do in a proper and structural way is you can do this. Okay? You can do this first. Instead of directly approach the parametry. Okay? Because if not, then you broke the rule that this x is this y is function of x. I hope you understand what I mean, okay? Okay, so what will happen here is this will take on the subject here. This will take on the subject here. So if you have this is not the equal with this. Okay. So to get to the concavity, you can go to this approach here. Okay. Okay, I think we'll just stop here for today. We'll maybe a review and going to some practical approach for this calculus part next Friday. So yeah, I think that's it for today. Yes. Which one? Whole? The whole thing? Or is it too small, or maybe just here? All? Okay, if there's no questions, let me stop the recording.